Hello everyone. Sawadee krap, namaskar. Welcome you all to Technobiz Rubber Tech Talk. This is a Technobiz virtual event series for the rubber and tire industries organized by Technobiz on regular basis by inviting well-experienced rubber technologies specialists. And we do have sometimes we have presentations on the technical presentations. Sometimes we do have discussions, conversations with the business people. So we all cover about what are the requirements, what are the needs of the rubber and tire industries. So today our topic is very useful and very important topic, how to develop retread tires of similar performance with the new tires. I think this is a very useful topic for tire industry people, and we have a guest speaker, Mr. Sabarinadha Prasad. Is well experienced, more than 35 years experience in this line, and is currently the managing director of the Revotech Treads based in India. So he's going to give a talk on how to develop retread tires of similar performance with new tires. So join me to welcome Mr. Prasad to give a talk on this topic.
Thank you, Param. Very warm good evening to all viewers. I am Sabarinadha Prasad. I got about 30 years experience in tires as well as retread rubber industries. So today's presentation is on how to develop retreaded tires of similar performance with new tires. So these are the main contents. Overview of retreading, retreading technology, how to develop similar performance with the new tires. It's a vast subject. So I will be trying to explain in simply understanding and interesting. I'll try it. So it covers tire retreading, retread rubber materials, or retreading processes, its challenges, then coming to retreading technology, compounding, tread rubber patterns, manufacturing process, pre-cure process, then a case study, how to develop similar performance of new tires. Okay, based on reverse engineering, product model, testing, field performance evaluation, product validation. In retreading, as you know, when a tire is worn out, maybe after 50,000 kilometers or even 1 lakh kilometers, we got two options. We can go for a new tire, replace it, or retread. Just replace the worn out portion of tread by a new piece of rubber and giving tire a new lease of life. The process these days is tire retreading, and the materials used for this process are called retreading materials. The important retreading materials, of course, pre-cure tread rubber, the fully designed, fully cured material, and hard rubber, slab uncured material, and bonding up a thin layer of rubber film, and of course the solution and tire patches. Retreading processes. Wherever there are different processes of retreading, pre-cure tread process, hot rubber, ring tread, RB tread, vacuum, etc. In pre-cure process, the worn out tire first is inspected for defects, and it is buffed to remove the old tread pieces. And after buffing, we apply a cement solution to get the surface. Then after drying the cement, we'll place the pre-cure tread, a long piece of tread, and it is curing in an electric chamber or steam bonder. In hot cure process, the difference is there is no designs. It's uncured material. It is not cured. It's a hot process because it needs more heat compared to the pre-cure process, this cold process. ring tread. Ring tread, the difference is we are placing a ring-shaped tread over the tire casing. Okay, then there are no splice is required. Orbited. Orbited, it's mainly used for OTR tires, big tires, where a small strip is extruded and it is wound over the buffed tire casing for the required dimensions, and then it is covered similar to malt cure or hot rubber. Vacuum leg. Vacuum leg similar to hot cure. The difference is we are using the segmented molds. You get better uniformity. Challenges. See the challenges in retreading. Belt separation, ply separation, tread lift, channel crack, chipping, cutting, low mileage, cost. The tread separation. See the tread is totally separated from the tire. Tread separation. Belt separation, belt got separated. Breaker, inner ply, outer ply, separations. Buttress crack. The crack is developed at the buttress of tire. Channel crack, the main complaint for retread rubbers, channel crack. See, a crack is developing in the groove and it propagates the entire circumference of tire. And finally, the tire is getting separated. Then treads shoulder separation and subsequent burst. If shoulder separation is not noticed, subsequent tire will burst. So because of these aspects, even today, the retread rubber got challenges in the market in the following applications. Long haul applications, when tire is running for long distances, it may fail, chance of failure. Non-stop applications. And the trucks containing perishable goods like agricultural producers, apple, pineapples, people travel long distances without stopping. And heavy road conditions, risk is there. Severe mines, as well as high temperature environment. So for these applications, still today, retread tires are not preferred by all customers. See, the major reasons for treated failures. So I classify into 4 aspects. One, the tire inspection failures, the quality issue of tread rubber materials, the retreading process failures, and tire vehicle operational issues. See, the inspection part, the tire before retreading, we have to inspect properly the tire is retreadable or not. If the tire has got major complaints, we have to stop. We are not supposed to retread it. If a tire retreaded having earlier defects, it may lead to problems. So the inspection is very, very important. Maybe small cuts, air entrapments, this unnoticed, this may aggravate in after running, after retreading. Similar tire patch, incorrect tire patch, or even repairs are not perfect. It may lead to retread tire failures. And quality issue of retread materials. The selection of tread rubber size, its dimensions, type, compound excess heat buildup. Generally, in India, what see, retread rubbers, the mileage will be there, but the tires are not running for long distances because of excess heat buildup. Bonding issues, bonding revision, poor tank of bonding, cement contamination. These all will lead to retread failures with respect to tread rubber material quality issues. Retreading process failure, puffing radius. Every new tire has got a put a buff radius, thread arc radius. So we have to, while buffing the tire, before retreading, we have to match the radius of the original tire. Otherwise, the thread won't match. It won't sit properly. And the pivot time and temperature is not correct. Then again, we got a differential pressure while retreading. The difference of pressure between the chamber as well as the tire. That is a DPZ. The DPZ is not mentioned properly. It can lead to issues. Vacuum under the envelope not given properly. It can lead to tire failures. Envelope, loose envelopes, leaky envelope can lead to issues. Similarly, tire and vehicle operation issues, so overinflation, underinflation, overloading, non-stop driving, impact, spinning on objects. Sudden impact on objects will get failures. Similarly, suppose the tire is stuck on an object. If we accelerate, the tire will spin there itself. It will create high heat and quality issues, alignment issues, suspension issues. So these are issues are there for retreading failures. Retreading technology. See, technology applies the right combination of science, engineering, and art to develop a successful product meeting customers' requirements of cost, quality, and sustainability. See, it has three aspects. It's science aspect, the science of raw materials, the structure, property, relationship of raw materials, the raw materials, physical and chemical characteristics. It has got a great impact on the product quality. Then engineering of process, the engineering of machineries, got a very good impact on product quality. And more important, the art of making product. So these three aspects we have to combine to make a successful product. So retreading technology has got these aspects: the rubber compounding, thread pattern designs, manufacturing process, the retreading process, of course, education, training, and applications. Still, the awareness of people regarding retreading is limiting its usage in the industry. So a lot of education training required in this aspect. Compounding. So I'll cover a brief of compounding. Compounding, basically, the rubber compound contains basically polymers, fillers, protective systems, vulcanization systems, special purpose materials. For retread materials, for thread rubber, we can use natural rubber or blend of natural rubber with SBR or PBR for a tri-blend. Mostly for highway application, we prefer a blend of natural rubber and PBR. For all of application, we can prefer a major part of natural rubber and PBR. For all after an OTN application, it's always better to go for a natural rubber plus SBR blend. And bonding or cushion, naturally bonding and cushion 100% natural rubber. And we can use a small PGBH or SBR 1712 for getting more easy poly release. Envelopes and curing tubes, mostly nowadays chlorobutyl, and tire patches, people use natural rubber, SBR, chlorobutyl. Reinforcing fillers. The reinforcing fillers are the strength-giving materials. Now, these are responsible for giving tire the strength. So, thread rubber, historically people use N330, N339, N220, recently in 234 complex. And latest complex like in 134 we can use or BC2109, or even silica we can use for reinforcing builders for thread rubber. And bonding mostly people use N660, N550. We can also use N330. Envelope and curing tubes, N550. Protect system. Thread rubber, we use antioxidants, and wax. Bonding and cushioning mostly we use antioxidants. Envelope, as it is chlorophyll based, not required. Tire patches, antioxidants are used. Then vulcanization systems. For vulcanization, it is always better going for low sulfur systems for thread rubber. Low sulfur systems will give you mostly monosulfuric crosslinks. Monosulfuric crosslinks means the link contain only one sulfur atom. This is more stable towards heat resistance. And bonding for getting good bonds and storage life, we use insoluble sulfur. Envelopes normally sulfur less, no sulfur, sulfur less curing. Tire patches, ultra fast accelerators are used. Even room temperature curing systems are used for tire patches. Process aids or special purpose materials. There are materials like coupling agents, like silane coupling agents, or anti-reversion materials are used for thread rubber, for getting more life. Bonding for getting better bonding, resins, and adhesion promoters. See, thread rubber quality, it has got three aspects. One is the quality of thread rubber material. Second is the quality of retreading process. Finally, the application and operating conditions of tires. See, the same thread rubber, the same composition, putting in two applications. One application on the left side, highway drive application, long highway drive, is getting 100,000 miles. Whereas city driver, it's getting only 10,000 miles. So same material under different conditions. One is non-stop, plain road, normal load, low temperature, leading to good mileage. The same material under different conditions resulting 1/10 of mileage. So the mileage is a highly complicated phenomenon. It depends on a lot of factors. Let's see. The factors influencing tire wear: driving conditions, road conditions, vehicle conditions, tire conditions, the design elements. See, driving conditions, even there are free rolling. Even free rolling, say tire wear is basically because of slip. Slip means the relative movement of tire surface and its road. If there's a relative movement of the tire surface and the road, then slip is happening, friction is happening, resulting. So the tire getting wear. When accelerating braking, the slip is chronic. Even cornering, slip is more. And road conditions, the plain, hilly, off the road. Vehicle condition, load of the vehicle, speed of the vehicle, alignment, suspension, tire conditions, insertion pressure, temperature, sidewall stiffness, belt stiffness. It has complex parameters affecting tire wear. The design, tread element shape, tread block arrangement, tread block interlocking. So these all aspects directly influence the tire wear. So same material can lead to different performances under different conditions. TED designs. So the compounding was the first aspect leading to TED performance. The second most aspect is the TED designs. TED designs. The TED is that part of tire that which comes in contact with the road surface where the tire is rolling. The designs basically give the grip for the tire. There are a lot of other parameters with regard to TED designs. The type of TED designs, grip designs, leg designs, grip leg designs. In rib design, the TED elements are oriented in the longitudinal direction. So it will give you very good longitudinal traction. So it is mostly used in steer wheel tires. It has got better steering response. See, the right is the contact pressure distribution. See, the red indicates maximum pressure and the blue indicates less pressure. So the contact pressure distribution depends on tire design. It's a leg block design where the designs are the TED elements are oriented in the lateral direction. It gives better lateral stability and traction. So it is mostly used in traction wheels or rear wheels. Rib leg, semi-leg, it's a hybrid of both rib and leg designs. See, let us briefly, quickly examine the TED design criteria for TED design elements and the tire performance parameters. In TED design, these are the parameters: seal and ratio, void ratio, groove depth or non-skid depth, groove width, pitches, slit width, slit angle, shapes, shape density, block arrangement, size and shape of TED elements, interlocks of TED elements. So these are the TED design criteria, TED design elements. So these are TED performance, tire performance parameters: traction, grip, dry stability on the dry road, wet stability on the wet road, ice stability on the ice roads, aquaplaning, and tire wear, mileage, steering response, noise, comfort. So we can correlate with the TED design elements impact, how it impacts on tire performance, TED performance. That's it. The TED design criteria vs tire performance parameters. Void ratio. The void ratio or the seal and ratio or the net contact area all are almost similar or related terms. The higher the void ratio, so what happens? Higher the void ratio, see, the contact pressure on the area will be high. The net contact area is less, so the load is distributed on the lesser contact area. It leads to higher intensity of contact pressure on the contact patch. So it will lead to higher wear rate. So high void ratio leads to low mileage. Aquaplaning. Aquaplaning is when a tire is running on a wet road. There is a water film is formed between the tire and the road surface. Consequently, a hydrodynamic force is developed between the tire and the road. As the speed increases, this hydrodynamic force increases. And when this hydrodynamic force exceeds the inflation pressure, the tire virtually loses its control. It virtually moves over the water, like a boat in water. At any point of time, the tire can lose grip, it can skid away. That speed is called aquaplaning speed. So the void ratio is high, the water can be easily drained off. To higher the void ratio, aquaplaning improves. Similarly, snow traction. The void is more, the snow can be easily drained off, so snow traction improves. Pattern noise. Pattern noise, see the pattern noise mainly because of the quantity of air entrapped in between the road and the tire. The more void ratio, more air entrapped, so the more noise. So as the void ratio increases, the wear performance, the mileage reduces, aquaplaning improves, pattern noise worsens, snow traction improves, and dry stability also worsens. So normally, the net contact area for different application tires, the highway steer wheel tires, 75 to 85% is the net contact area or the sealant ratio. For highway drive axle, 65 to 75%. Cone of application, 60-70%. And OTR, it's 55-65%. The net contact area for different applications. And groove depth. So groove depth, we say NSD, the non-skid depth. Same thing. Okay. So naturally, the groove depth increases, more mileage. Snow traction improves. Pattern noise, more oil is, more air entrapped worsens. Aquaplaning, the water can be drained off easily, improves. Dry stability worsens. See, tread design groove depth NST. For the applications, highway application NST of 15-17 millimeters for steer tires, grip tires. Highway drive axle tires, 70-20 mm NST. Mixer application 20-22 mm NST. And OTR, big OTR tires 22 to 50, even more. Depth will be there. Groove width. Similarly, groove width increases the mileage, wear performance worsens, pattern noise worsens, aquaplaning improves, bed stability improves, dry stability worsens when the groove width is increasing gradually. Number of pitches. More number of pitches, naturally snow traction improves, pattern noise improves, dry stability worsens, comfort improves. Selectivity. Wider selectivities, wear performance worsens, pattern noise worsens, aquaplaning improves, bed stability improves. Okay. Slit angle. Slit angle steeper. Slit angle steeper, the wear performance improves because it provides less resistance to tire while running. Stripe density. Snow traction improves, pattern noise improves, bed stability improves, dry stability worsens. And block arrangement. See, the careful block arrangement is basically for the noise control. And again, see the block arrangements, the tread block arrangements. If the tread block are interlocked means the one tread block is surrounded by another blocks. There's a tie bar between the blocks. It will resist the thread element squiming. It will allow the thread to vibrate while running on the road. Squiming, and you reduce tire wear. And geometry of thread block. Most important, the geometry of thread block. See, geometry of thread blocks should be in such a way that when the load is coming, tire is compressing on the footprint. See, rubber is not compressible, but rubber compresses. It expands to the different areas. So we have designed the thread block geometry, the shape in such a way that when the thread is compressed to the footprint, there shall minimum movement of thread element on the roadside. The shape should be such a way the element movement shall be off the road surface. It will reduce slip and friction. So these are the relation between the thread design criteria and tire performance parameters. Some typical thread designs, leg design, nylon threaded leg design, semi-leg design, radial grip designs, three-leg designs, radial block designs, mines, OTR tire, winter tires. See, winter we can see a lot of types. Winter tires. Bonding. See, bonding is a very, very important material for retreading bonding. Thread. For example, we use a 12 kg thread. The bonding is about 1 kg, 1.2 kg. The bonding the main purpose of bonding is to bond the new thread with the old casing. It's a very critical material in tire retread. Based on rate of cure, it is classified with 3 different categories: normal curing bonding, fast cure bonding, ultra fast curing bonding. So based on cure rate, we can reduce the cure time in the electric chamber or cure time of retreading. At the same time, the cure rate increases, the shelf life reduces. Bonding performance properties. Softness. So it is soft. Bonding should be soft. So we have to control the viscosity and specific gravity. Tackiness. Tackiness got 2 aspects: the adhesion and cohesion. Adhesion is a surface phenomenon, is adhesion of the bonding surface to the tire surface. Cohesion is the intrinsic strength within the bonding molecules. We need both for getting good tackiness. Good adhesion, good cohesion. Stretching. The people need to stretch bonding by retreading. You should have good cohesion for get good stretching. Cure rate, we have to control. Bond strength. Should have very good bond strength between rubber to rubber and rubber to metal. Revision resistance. So while tire is running wrong application, most of applications, the bonding has to have very good resistance to the heat. Otherwise, it will separate. Poly releasing. Well, while applying, the bonding should easily come up to the poly. Heat history, shelf life, the bonding has to keep for 3 months, sometimes 4 months before using. So it's a very good shelf life. The heat history should be very good. Manufacturing system, mixer automation. So we have covered compounding aspects, thread design aspects, and bonding characteristics. Now the manufacturing system, mixer automation. So mixing is a very critical process in any rubber good manufacturing. So basically, we classify mixing ingredients into 4 categories: rubbers, carbon blacks, oils, and chemicals. Rubbers These are in different geometrical shapes, physical states. So we have to mix these materials into a homogeneous mass. So mixer automation, automatic selection, feeding, weighing, and mixer control will give you very good consistency in mixing, very good batch to batch consistency in mixing. It will give you very good product. And manufacturing process innovation. See, normal conventional manufacturing process has got 4 to 5 stages: mastication, master batch mixing, repass mixing, final mixing, extrusion, then curing. Okay. See, we can undertake all the 5 process in a single stage: simultaneous mixing and online extrusion. So it will give you a lot of energy saving, huge savings in machinery, manpower, energy, time, but lead to good quality also. See, every stage, mastication, we are mixing rubber. The rubber molecules undergoing shear. It is broken into pieces. Master batch, again, it is getting heated. Master batch. Repass, again, the rubber is getting heated. Final batch. So every stage, the rubber, its molecules are heated up. So heating will kill the molecule's strength. So simultaneous mixing, master batch, final batch, and extrude simultaneously. Aging we can give at the end of the cycle. Not necessarily we should give every stage aging. Give aging at the end of the cycle. See, basically aging is given for the molecules to get back into the original stage. So this is the latest techniques, integrated manufacturing process, simultaneous mixing, extrusion, and process. Next is the retreading process. So retreading process is very, very critical. This is a retread chamber, electric chamber. The man is loading the built-up tire into the chamber. So people uses the different conditions. So we can optimize the cure time and temperature by thermocouple studies in electric chamber. Let's see. So the steps, you set up a reference temperature, maybe 125 degrees centigrade, the normal temperature of retreading, and develop an equivalent cure chart, and find a draw point of bonding. The draw point is the point at which the porosity is C. Then make a thermocouple tire, put in the chamber, take the time temperature data, and from that data we can work out the progressive QR or QR equivalence. This is the temperature time data. The red is the bonding temperature inside the type electric chamber. And the blue is the chamber temperature. The chamber temperature, we know the chamber is 125 degrees centigrade. It's almost from the beginning, the 0 time. The first is time, 0 is a time, 0, 5, 10, 15. We are noting temperature up to 130 minutes. Second, chamber temperature is set chamber 125 degree. And bonding temperature, bonding initially is cool inside the tire. So the temperature has to reach the bonding up. It has to cover the thread rubber section to the bonding point. So initially the temperature is very less, so gradually it picks up. And from this data, we can work out the equivalent QR. For bonding gum, an equivalent cure of 25 minutes is maximum. It's essential. It's enough. And after curing, just peel up the thread. See the bonding. If the bonding is paka or not. No porosity, no sponginess. And normally the cure time is set. The cure time is a blow point time plus safety time. Normally, 20% is given safety. Suppose your the blow point time in the curing chamber is 1 hour. You put 1 hour, 1.2 hours. Okay. Now this is a case study conducted over 3 years to develop retreaded tires of similar performance in new tires. The development study got 5 phases. The reverse engineering. See, extended reverse engineering done on new tires of all leading brands, including international brands, as well as the competitors whatever. Extensive reverse engineering. Yeah. And based on the output of reverse engineering, we made a product model. And the product model was analyzed in the internal laboratory as well as external laboratory. Then sample products put into tires and the field performance evaluated against in comparison with the new tires. Then finally, external verification done for product validation. So we'll slightly describe these 5 stages. The reverse engineering techniques for tire composition. These tools are used for reverse engineering for identifying the thread composition. FTIR, TGA, DMA, physical mechanical analysis, and chemical analysis. By these 5 analyses, we can arrive almost 99.99% of compound composition. What kind of rubber, what kind of carbon, pillars. Let's see. FTI. FTI is mainly used for the chemical composition of substances. So every chemical composite got typical peaks. So a typical NR spectrum is given. Okay. So from this analysis, we can identify the polymer nature, whether the compound contains 100% natural rubber or a natural rubber PBR blend or natural rubber PBR SBR blend or PBR SBR blend. So we can identify the polymer content. What kind of polymer is used for thread rubber tire from FTIR? FTIR mostly done in rubber bore. And TGA, thermogravity analysis. It measures how a mass of a material changes mass over temperature. Because in rubber compound, we got different rubbers, carbon black, zinc oxide, stearic acid, antioxidants, accelerators, wax, sulfur, lot of things. So these materials decompose in temperature varies. So TGA, so we are measuring the mass change over time and temperature. So from this analysis, we can come to know the rubber hydrocarbon content. See the first part, you can see the first part, the 13% is basically the volatiles. Volatiles basically our antioxidants, accelerators, stearic acid, sulfur, oils, etc. Okay. Then comes the polymer. Different polymers got different decomposition peak. For natural rubber, 370 degrees centigrade. SBR 450 degrees centigrade. PBR 420, 460. Okay. So from TGA, we can find the rubber hydrocarbon content and polymer ratio from the area under the graph. And carbon pHR, oils plus chemical pHR, and the last residue will be the inorganics, zinc oxide, silica, and white fillers. From the mix of the residue, we can estimate by gravimetric analysis, zinc oxide, stearic acid, silica, and other white fillers. So almost 99% of the composition we can identify from TG and FTA. DMA analysis. So DMA analysis, the most important analysis in tire rubber see in DMA, a cyclic sinusoidal stress is applied on the sample. You can see the picture of pictorial representation of DMA. The host generator, the top, applies a sinusoidal stress at a frequency of 10 hertz. 10 hertz means it will move 10 times in a second. It almost similar to the tire operation. A tire running at a speed of 120 kilometers will have around 10 hertz cyclic compressions. And we can change the temperature. Set the cabinet. Temperature we normally change 20 to 120 centigrade, normally the tire operating temperature. And strain means the extent of the deformation. Normally tire is deformed around 10-15 millimeters while compressing on the road contact. So we took 1% dynamic strain. So from this analysis, we can find out the complex modulus, elastic modulus, tan delta. There's a typical DMA graph of a rubber compound. So the black one is tan delta. So the rubber got 4 phases: glassy region, glass transition region, and the elastic region, and the viscous region. The tire is operating within the elastic region, the third region. So normally a tan delta at 100 degree, a low tan delta at 100 degree leads to low heat buildup. And a low tan delta at 60 degree indicating low rolling resistance. And a high tan delta at 30 degree, high traction. And again, high tan delta at 0 degree, high traction. So tan delta is the most important parameter for tire performance evaluation with regard to heat buildup, mileage, rolling resistance, traction. It's a very important parameter for rubber compound analysis for tire rubber application. So this is the tan delta of different tire compounds. We got nearly 10 tire compound were test compounds, tan delta at different temperatures, tan delta base temperature. The elastic modulus base temperature. So we analyzed the competitors, tire compounds. We almost arrived their formulations and the dynamic mechanical properties. And based on those data, we made certain product models. And these products are tested in major laboratories. Aditya Laboratory, Taloja, Reliance Elastomer Support Center, Vadodara, Nasudri, and JJ Murphy Center, Kochi, Rubber Board, Phil, Lancet. So we made products and tested in almost all major laboratories and analyzed the entire properties, all properties, rheometric properties, viscoelastic properties, viscosity, mechanical properties, all properties we analyzed. And just the critical properties they tabulated. Even though we made n number of compounds, only the reference compounds, typical compounds, development 1, development 2, development 3 is given. So the results are given. See, the control compound is a tri-blend. First compound is a tri-blend. This one is a 40, 40, 20, 40 pHr, natural rubber, 40 pHr, PPR, 20 pHr, SBR, and of course carbon black N330. And development number 1 is 80-20, 80 NR, 20 SBR, and N22 carbon black. And development number 2, 80 NR, 20 PBR, and N230 for carbon black. The last one, 100 natural rubber, 100% natural rubber, N130 for carbon. So the properties, modulus 100%, modulus 300%, tensile strength, elongation, TF strength, hardness, then cut chip resistance. It's very important property, cut chip resistance, the diameter loss, aberration index, ARI, heat buildup, and dematerial cut growth resistance. This is a very, very critical parameter for tire performance. It has a very good correlation with the tire performance, tire mileage. Dematerial cut growth resistance. What we are doing is we are measuring how many kilocycles of flexing required for a growth of 2 mm to 12 mm. For a cut growth of 2 mm to 12 mm. See the last compound, 100 kilocycles. The first compound is 22 kilocycles. So the last compound has got almost 5 times the cut growth resistance. The tangent vector. At 30 degree, 60 degree, 100 degree. Okay. And next is the field performance evaluation. So based on the product model and the external laboratory testing, so we made some product and tested in trucks. See, the development tire has got 45,000 to 50,000 kilometers. All the 8 tires. All the 8 tires on the rear axis of the far bench got 45,000 to 50,000 kilometers. But the original new tire was only 22,000 kilometers. So the development tire got almost twice the performance of new tire. See, this is the testing for chipping and cutting resistance. See, the left one is a regular material. The right one is the development material. So the right one, see, you can see the clean tire wear, like a glass. No chipping, no cutting. Okay. This is the compilation of the field performance analysis conducted for various applications. Vehicle application, a pattern used. Pattern means the pattern semi-like 240. Semi-like 240 size. So the development tire, the mileage 1 lakh 3,791 kilometers, whereas the new tire is only 70,000 kilometers, 48% excess mileage. Like different applications, highway application, heavy mines, heavy mines, heavy mines, heavy mines, heavy mines. Okay, there are different brands of new tires. So in all testing, all field performance testing, the development tire got nearly around up to 30-40% more mileage than the new tires. Then the last stage, so based on the field performance evaluation, we got better performances. So we decided to have a third-party validation. Third-party validation, we made products with the development compounds and tested against new tires in 6 applications. It was done by rubber board under the supervision. So in all applications, it has got from 10 to 50% more mileage than the new tires. This is the original certificate for rubber board, certifying better performance than new tires. So I will conclude how to develop retreaded tires of similar performance new tires, similar or better. So we got 4 aspects: compounding aspects, tread design aspects, manufacturing system, optimization, thermocouple. Compounding. Compounding. So we selected high performance carbon black and silica, a combination. Then optimal level is the filler loading. The filler loading is very, very important. The percentage loading of carbon is very, very important for the tire performance. And low sulfur vulcanization, anti-reversion, filler coupling mechanism. These 4 aspects we applied in compound design. And tread design for minimizing tread element squaming by giving interlocks between blocks. And uniformity in contact pressure distribution by providing same buffing radius, required size, and optimizing tread element shapes for minimum friction. And of course, manufacturing system, mixer automation, and process integration. Optimizing cure by thermocouple studies in electric chamber. Thank you for your patient hearing. So see, I went through the entire slides quickly. So any doubts, we can ask in the Q&A session, or you can contact me, or you can contact Param for further clearing.
Thank you very much,
thank you.
Mr. Prasad.
Yeah.
Thank you, Mr.
Yeah.
Prasad. Please stay on. Please stay on, guys. This is a very good presentation, nicely described with all the key features of the retreading process, how to make it a similar performance new tires. It's a time to ask questions. There are some questions already from the audience. Let's look at those questions one by one. In the meantime, if you'd like to ask any further questions, feel free to ask the questions. Please do make sure that type your question in full, yeah, so that he can address it appropriately. Please stay on. Let me show you on the screen. Please read the question. Now the question is shown on the screen. Please read the question and answer it appropriately, Mr. Prasad.
The vulcanizing solution is used for wetting the tire surface for bonding with the bonding arm. So just wetting the surface after buffing. Okay. Wetting will give you better bonding between the bonding arm and the old tire. The old tire surface is dry. Okay. So that bonding arm can penetrate the industry between the tire surface. To give you lead to better bonding between the bonding arm and the tire surface all the time. Yes. See, in Indian retailing sector, now there is a tendency is coming to the trend is coming to the quality tires, the quality of tires. Of course, the future is good for retailer tires with quality.
Is asking about, how is the situation now in India in terms of the quality and the cost when it comes to the comparing with the new tires? Are they in the direction? Yeah.
See,
Please comment. Yeah.
you can see now. See, at a cost of 30% of new tire, we can retread a tire. At a cost of 30% of new tire, we can retread a tire. With 30% of the cost, we can get almost same performance of new tire. For example, a new tire is costing around 20,000 rupees. We can get a tire retreaded at a cost of 6,500 rupees with same performance of new tire. Okay. See, yes. In USA as well as in Western countries, about 80% tires are retreaded. In India, still less than 50% tires are retreaded. So that scope is there for retreaded to cover more tires. It's only 50% now, less than 50% compared to 80% in US. Okay. See, the major difference between the hot and cold. See, I can say you the hot process, the hot material, we have to keep the material for a long time, maybe 2 to 3 months. And the cold compound is using as and when. Basically, the compounds are same. Only difference in hot compound, we are using insoluble sulfur for more shelf life. Otherwise, compound is almost same. Number one. Number two, in hot process, we have to maintain slightly lesser viscosity. Otherwise, the compounds are almost same. Okay. The compound depends on application. Yeah. Okay. Yeah. PCR tires. See, in European countries, now the PCR tires are retreaded mostly. In India, still the culture has not come to that mark. Maybe retreading 5% PCR tires, but we can, of course, we can retread PCR tires for getting performance. Sure. In Europe countries, they are using it, PCR tires, passenger car tires. So soon, people can use. Yeah, soon, very soon, people can use. So ring tread, actually ring tread introduced in India. 5 years back. It is a good product, but the market didn't click. So I prefer Retread will work. Okay, we are work on it. The people didn't interested in Retread introduced. Okay, Retread technically is a good product. It is good. It is spliceless product. But even then, we got splices in pre-code setup. The splice failures are very, very negligible. Splice failures, if you splice properly, pre-code setup, splice failures are very negligible. But Retread is good in case of splice weak. Okay. Yeah. The anti-regression agents we used. I use it. There are two kinds I use. One is silent. Silent coupling agent has got anti-regression properties. Number one. And Volcuran is the best material for anti-regression properties. Volcuran. Pergalink is there, but Volcuran is good. Okay, Volcuran is the best. Then silent has got anti-regression properties, of course, Pergalink. But Volcuran is the best. Okay. OTR tie is the most important property, the cut chip resistance. Cut chip resistance and heat resistance. See, for cut chip resistance, we need natural rubber has a good cut chip resistance properties. Again, the cut chip resistance sometimes we require along heat resistance, especially loaders in furnaces, blast furnaces, loaders. That have to we need both cut chip and heat resistance. So we need a blend of natural rubber and SPR. So these two proper cut chip resistance as well as heat resistance. OTR ties. Okay.
Okay, that's all the questions we have, Mr. Prasad. Thank you very much. It's a very interesting presentation, informative. Before I let you go, would you like to give a final remarks to the audience? Final message to the audience, please.
Yeah. Okay, yeah, good. See, retreading is a very good option for increasing tire life. We can retread with good technology. We can have the same performance of new tires in terms of mileage, reliability, safety. Okay, even there was a research study conducted by in America, a National Highway Research Authority. So they have found for retread rubbers are as good as new tires. There is no quality issues or there is no reliability issues in retread tires. So retread tires has got a very good future. With the extended product liability that legislation is coming. So the retread rubber future is good, provided the quality has to be good. The people has to. It's not a cheap product. We have to as an alternative to tire. Okay, then the future is good. The scope is good. So retreading is a good practice for even environmental protection. Okay. Thank you.
Okay, thank you very much, Mr. Prasad. Excellent presentation. I would like to invite you in the future sessions of the Rubber Tech Talk. Thank you very much once again.
Thank you, sir.
Okay, guys, that's the end of the presentation of the today's episode of the Technobiz Rubber Tech Talk. How to develop retreaded retreaded tires of similar performance with new tires. I hope you find this session useful to you. Look forward to welcoming you in the future episodes of the Technobiz Rubber Tech Talk. Thank you all. Bye bye for now.